For our project, we researched the Maria Pia Bridge, now referred to as an International Historic Civil Engineering Landmark by the American Society of Civil Engineering Landmark Program. The Maria Pia Bridge can be considered many types of bridges, including a railway bridge, a two-hinged arch bridge, a truss arch bridge, or a deck arch bridge. Looking at the map shown here, you can see that the Maria Pia Bridge is located in the northern part of Portugal on the west coast, close to the Atlantic Ocean in a city called Porto. And now zooming in, you can see the Maria Pia Bridge was built to connect Porto and Vila Nova de Gaia in Porto, Portugal, by crossing the Douro River. Currently it sits between two other bridges, the São João Bridge and the Infante Bridge. The Maria Pia Bridge was designed by Theophil Seyrig, Manuel Afonso Espergueira, and Pedro Ignacio Lopez. The bridge was then engineered by Gustave Eiffel, who is known for many other structures, including the Eiffel Tower. The bridge was built using a new technique that sped up the process of constructing the bridge that was thought of and implemented by Eiffel. Construction of this bridge began on January 5, 1876. Construction was done by Eiffel and C. de Paris and continued for more than a year. Made up of majority of iron, the construction process was very interesting. The construction process began building from both sides and finished by meeting in the middle. Wires were used that extended from the shores of the river to assist in the construction of the arch. Supports were also constructed that held the piers which were built to help support the arch. All of this construction was completed on October 8, 1877. The Maria Pia Bridge became the longest iron arch bridge in the world at the time of its construction. Soon after construction finished, the King of Portugal opened the bridge and made the decision to name the bridge after his queen, Maria Pia. The Maria Pia Bridge was used by trains and railway services across the Douro River until 1991, when it was shut down and the rail services were transferred to the São João Bridge just southeast of the Maria Pia. Knowing that the Maria Pia Bridge is out of service, we can look back and think about how the bridge performed over the years. While no major upgrades were needed, the bridge did its job and successfully kept the rail services running and provided a safe path for trains to travel across the Douro River. The Maria Pia Bridge was a beautiful structure, and while it never happened, there was a plan made to relocate the bridge to the middle of the city of Porto and make the bridge a monument to the city. I think the fact that there was a plan to do this shows the importance and greatness of the Maria Pia Bridge. And now we will hear from Meredith Shaw, the designer, Ellie Sealock, the builder, and Jared Evans, the manager, about their roles, procedures, and challenges they went through with this project.
Hi, my name is Meredith Shaw, and I'm the designer for Group 15. I analyzed the Maria Pia Bridge using STAAD rather than SAP 2000 because I felt like I could do a more effective analysis with a software I was comfortable with. I built the model with a length of 354 meters and 5 piers and a curved arch. The upper deck I designed as a plate with a 54 by 6 generated mesh to help with the analysis. A lot of the issues that I had with the model stemmed from the lack of information we had about dimensions and material properties. The team and myself addressed these issues by making logical assumptions about the bridge based on dimensions we found on reliable sources such as bridgeinfo.net and Google Earth and looking at other pictures. It was just difficult to find these because the bridge was built in the late 1800s. I also used AutoCAD to accurately depict the arch and the piers. And instead, there is an option to generate nodes equally spaced, so I used that for the piers. And then I assumed typical iron material properties, and for all the beams I assumed W44 by 262. I just wasn't really sure what to use for this, so that seemed like a safe bet since it was going to be holding so much load. I also assumed the supports for the piers to be fixed and the end supports for the bridge deck to be pinned. I had a difficult time finding information about the analysis online, so I did reference an article on the critical analysis of the design and construction of the Lewis I Bridge in Porto, which was designed at a very similar time to the Maria Pia Bridge, and it's also very close to the Maria Pia Bridge in location, so I figured it would be subjected to similar loads since it's in a similar environment. So I tested the bridge under a dead load of the structure as well as a live load. The two load cases I analyzed were for LRFD and ASD. Load combination 1 had a load factor of 1 applied to the dead and live load, and load combination 2 had a factor of 1.2 applied to the dead load and 1.6 applied to the live load. As you can see in the deflected shape in the attached report under the dead load of the structure, the middle of the structure deflects quite a bit, and that would not actually happen because it's just under the load of the structure, so that would not make sense. But I had a lack of information and wasn't really sure how to go about that analysis for that. I also had a difficult time connecting the curved arch to the bridge. As you can see in the deformed shape, it's completely just sagging the bridge deck and not at all using the curved arch to support it. To see the results for the bending moment, shear force, and the deflected shape, you can reference the report.
The construction process used by this group was in the SolidWorks program. First, the bridge deck and all of the pier outer structures were drawn. Next was to build all of the trusses on the bridge deck and the piers. A major challenge we had to deal with during this process was the whole bridge was made out of trusses, so there were many lines in this one document, and it took minutes to refresh every time the model was saved or a new line was drawn. Since this was such a major issue, we made a decision to only draw the trusses on the 2 main piers that are connected to the arch, as well as on the bridge deck, while leaving the arch and the outer piers as just a skeleton of them. The 3D printing process also did not end up working out for us. Going around to all the places on campus to 3D print, it was about a 2 to 3 week delay on the queue, which would not have let us turn it in on time. Also, the SolidWorks document would not convert over to an STL file, as the geometry used did not support this file type. This was because the lines had no width, but we could never figure out how to change that.
Overall, I think our group worked very well together and did a good job completing this project. Our biggest challenge, I think, was working with programs and software that we were unfamiliar with. We ended up having to ask for help from our TAs, and they were unsure how to help us. This resulted in hardships on our group in trying to learn the program along with learning about our bridge. Another challenge we faced was the bridge being so old it was hard to find exact records. With it being built in the late 1800s, we found no good resources that gave us exact measurements other than the total lengths. We made do with what we could find, but I wish we had been able to find a resource that would have gave us more exact information. Looking back on the project, our group worked extremely hard and did the best work we could with what we were given, and I am proud of how our project turned out.